except that instead of looking at what happens over a time interval of 3 months or 6 months or a year, I'm going to look at what happens over a time intervals of a few seconds or a few minutes. Okay? And obviously different methods. Because if you wanted to use the same method over 1 second, what do you think the transition density looks like? It looks like a direct mass. Okay? It looks like a point mass at x. And, you know, over 1 minute, an asset price isn't going to move a whole lot, and you're not going to be able to do very much interesting thing with that. So I'm sorry, I just mixed up the two references between the two lectures. So this is the paper for the other one. This one is a different paper, but anyway. So now testing for, one more thing I want to tell you. At low frequency, by the way, that method is completely agnostic about what type of jumps you have. The previous method is all about, well, that's a continuous process, or it's a process with jumps. So the previous method is very non-parametric in that. It requires no assumptions whatsoever. It requires no assumptions whatsoever on the nature of the jump process. It's basically a method that sort of is completely agnostic again about the nature of the jump process. Now, well, of course, at high frequency, we can perhaps hope to distinguish various types of jumps and talk about again, in the case of Levy processes, this distinction between sort of big and small jumps. And very clearly, large jumps are easy to pick out. It's like when you see them, you know what you're dealing with. It's a bit like things that are difficult to define but easy to recognize. Difficult to define formally, but like when you see something, you just know that this belongs to that category. But if you look at sort of evidence for the small or more frequent jumps, it's harder to tell. There were questions or discussions at the end of the previous session before the break about whether, and there are people who are strong believers in the presence of very small jumps. Or models that are purely discontinuous if you allow for very small jumps. So there are different types of jumps, and one of the things we would like to do is sort of, tell whether jumps are present or not on the basis of high frequency data. In a way, it's almost like a bogeyman, because I think everyone understands that jumps are possible. Whether they are present in a given time series is a different matter, but the fact that they are possible is clearly the case in finance. And it's also clear that they have quite different properties and implications for financial modeling. For market completeness or incompleteness, for how you would price an option and hedge it. If things are continuous, you can do things that are relatively simple. If things are discontinuous, then you need to start thinking about alternative methods, and so on. Okay, so there are different types of sort of jumps. So the first paper is the one I just described. The second paper is the one I talked about in response to Dennis's question about using also options. So Carl and Wu also use options, but in a different context. They look at the behavior of very short-term options that I described, and they look at how they converge, how the prices of options converge to, an option converges to the hockey stick payoff at expiration. So when you have very short time to maturity, you converge to the hockey stick payoff. The question is, you converge differently if the model is continuous or the model is discontinuous in the limit where time to expiration goes to 0. And that's what they are exploiting. What I was exploiting is also options data, but I was exploiting options data differently. I was taking options data not at an infinitesimal maturity, but at 3 months, 6 months, a year, various range of maturities, and then looking at that criterion function for the risk-neutral distribution that's implicit in the price of option. The third class of papers, I guess, correspond to the literature you were referring to, which is about testing for jumps by splitting the quadratic variation into a continuous and a discontinuous part using things such as, for example, bipower variation, which is the idea of using adjacent returns to get a convergence to the continuous part of the quadratic variation. And so you can test for the presence of jump by seeing whether the total quadratic variation is close to the continuous part of the quadratic variation. One issue with doing a test like this is that if your null hypothesis is that jumps are present, it's not clear how you formulate that null hypothesis, because then you have to say, okay, my null hypothesis is that continuous part is 80% of the total quadratic variation, or 90%, or 70%, or how do I decide what is my cutoff for deciding that jumps are present or not? Lee and Micklin is yet a different approach that uses, it's a different approach that tests for jump uses effectively different thresholds for measuring jumps, and then you can construct a statistic out of that way. Jeong and Newman is yet another approach that's based on the cost of replicating a variance swap and figuring out whether the replicating cost of a variance swap matches what you get if you have a continuous model versus a discontinuous model. And you would end up with actually an additional term in the case of a discontinuous model, and then you can test for the presence of that. And then since then, there've been yet another different types of models, but my sort of slides are written as of when we did that paper. Okay, so what I'm going to talk about now is, again, the high frequency case of delta goes to 0. So that's kind of the extreme from what I talked about earlier. And I'm going to design very simple, what we did there was we designed a very simple family of test statistics that have a binary outcome. A limit of 1 in the continuous, in the jump case, and a limit of 2 in the continuous case. So it's a very simple test statistic, and it's a fully non-parametric test statistic in that it does not require, first of all, it works for general semi-martingales, but also it doesn't require that you estimate any of the characteristics of that semi-martingale. So it's a general semi-martingale, and yet you're not sort of required to specify or estimate the stochastic volatility, see whether there are jumps or not in stochastic volatility, and that sort of thing. Also, a distinguishing feature of that test, I suppose, relative to the other literature, is that we're doing the test for both ways. So we're doing the test where there's a test for whether the null hypothesis is that you have no jumps, but there's also a test where the null hypothesis is that you have jumps. So it's a symmetric treatment. So we're not asking you to take a stand as to what you think is the natural case in your problem. And coming back to sort of questions that were asked earlier, some people might think that the natural null hypothesis is that jumps are present. Some people might think that the natural jump hypothesis is that jumps are absent. And that might come either because they have philosophical differences as to the right way to do modeling, or it might come simply because they're thinking about different data. But in different data, I suppose the natural null hypothesis to think about would actually be different. So it works as soon as you have a semi-martingale. It's a much weaker condition than what's usually assumed in this, and again, you don't require to estimate anything. So the setup is that you have a semi-martingale. So you have a process that is decomposed into a finite variation process and a local martingale. So basically, you have a continuous part and a jump part to each one of them. And in the case of a stochastic volatility model, for example, MTC would be your integral from 0 to t of sigma s ds. And the jump part would be the integral over x and t, and 0 to t, of x times the compensated Poisson measure that I wrote yesterday evening. Okay, so this would be a process that would be a semi-martingale. And the drift, the volatility, the jump measure are themselves possibly stochastic. They can possibly jump. So you can have jumps in the drift, jumps in the volatility, jumps in all sorts of different things. But we're interested in testing whether there are jumps in the asset price. Now, for technical reasons, we're going to maintain, at least under the null hypothesis where there are no jumps, we're going to maintain the fact that the Brownian, the continuous martingale part is never degenerate. So that there's always the Brownian motion is always present. Otherwise, under the null hypothesis that there is no jump, well, you can't do very much because your model becomes, well, you don't know what. If there are no jumps but there is no Brownian, a model with a stochastic drift isn't really a very realistic model for asset prices. I mean, it's just not capable of generating enough variation in prices. So the testing problem is that you observe discretely over a finite time interval 0 to t. As I mentioned, there is nothing ergodic in this. So you go 0 to t, t is finite, because otherwise a lot of those quantities don't even exist, or they converge to infinite limits. So clearly you need to go from 0 to t, with t finite, discretely observed at time I delta n goes to 0. Now if the jump measure is finite, that means if you have a compound Poisson process, right? If the jump measure on the whole real line is finite, then it's possible to have a Peso problem. I.e., since 0 to t is finite, let's say you have 1 month of data, it's possible that there were no jumps in a month that you're looking at, but jumps are possible. Now, the previous test I talked about is immune to that problem, because if jumps are possible, option markets would tell you that by skewing that smile up, and you would see that in the implied risk neutral density, even though there may be no jumps in the time series. I mean, in any given month of data, if you're not looking at September 08, it's quite plausible that you would not find any jumps. And again, that test, the one I'm going to talk about now, this one would answer no test, because that's a test that's designed to work on the time series of the underlying asset returns. It knows nothing about risk premium. Now, here are various measures of the variability of x that are going to be the mirror image of, for general semi-martingales, of the statistics I described this morning when I talked about those moment functions in GMM. We are going to basically be using absolute moments, as you will see, or power variations. Now, here are two processes that both measure some notion of the variability of the x process. A measures the continuous variability of x, and B measures the discrete variability of x. Remember that x is a Cadillac process, so it's right continuous, left limit. So delta xs, you have to be careful here. Delta xs is not the observed increment at time interval delta. Delta xs is a jump in x. Of course, I don't observe the jumps of x because I don't observe the continuous sample path. I only observe it discretely. So these are, at this point, just theoretical definitions. I'm not saying that these are things that I observe. So B of P is the sum of the pth power of the jumps, absolute powers, and A of P is that integral you see up there. Now, the quadratic variation is A2 plus B2. A of 2 plus B of 2, it's the sum of those two quantities. It's the integral of sigma squared dt, continuous part of the quadratic variation, plus B of 2, sum of squared jumps. Okay? So the problem, of course, boils down to deciding whether B of P is positive for any particular observed path with any given P. And now, if you introduce the observed increments of x, which may or may not be to a jump. Now, those are simply the log returns of the asset price over that short time interval, i.e. it's the asset price the next time you see it minus the asset price the previous time you saw it. Then, let's define the estimator B hat to be the sum of the pth power of absolute value of the increment. And I am not saying that B hat is an estimator of B. It will be for some values of P, but not for all. Clearly, if you take P equals 2, for example, That is realized volatility. And realized volatility does not converge to the discontinuous part of the quadratic variation. Instead, it converges, of course, to the total quadratic variation. So clearly, I'm not saying that B hat here is an estimator of B for all values of P, but it will be for some. And indeed, what you have at the bottom here is what happens to B hat. When P is 2, as I just said, realized volatility converges to the total quadratic variation, and that's what you have for all X processes, subject to regularity condition, but that's a very general result for pretty much all semi-martingales. And then you have the following considerations which come back to what I was describing this morning. When P is less than 2, maybe let me start with P greater than 2 first. When P is greater than 2, that's the one up there, then B hat zeroes in on the jumps. So in other words, you end up with just something that depends on the large increments. So the large increments dominate. It's a bit the same in the ergodic sense. It would be the same as saying that if you take higher order moments, you are sensitive to the outliers. Right? And the higher the order of the moment, the more sensitive you are to the outliers. This is the equivalent of that statement. If you sum the pth powers of the increments and P is greater than 2, then ultimately that converges to the contribution to the discontinuous variation. If on the other hand you take P less than 2, then after scaling, B hat does not converge to B, but instead it converges to A. In other words, it converges to the continuous part of the variation of order P. Now, that's with scaling. That's with scaling, and you see that the scaling when P is less than 2, this is the third equation. This is the third equation you see here. The scaling is such that, of course, B hat goes to infinity. So B hat diverges in this case. When P is less than 2, B hat diverges because you have too many increments. I mean, in the limit, all you have to do is convince yourself of what happens when P is 0. When P is 0, B hat is simply the number of increments. How many increments you have? You have n increments. Well, n is T over n, is T over delta, so this should diverge like 1 over delta. And indeed, after multiplication by delta, well, it has a finite limit. So that's what you're getting here. Now, interestingly enough though, if B is 0, if there are no jumps, if B is 0, then for all P's, this convergence remains true. So these two results are not incompatible, because when P is greater than 2, now, if there is no jump, then B hat goes to 0. This is what this is telling you, but you can get the next term on, which is now, this now becomes a negative power. For P greater than 2, this becomes a negative power of delta. So this is indeed showing you that B hat goes to 0, but after blowing it up at delta, you go to A of P. The bottom line is, P greater than 2, you isolate the jump component. P less than 2, you isolate the continuous component. P equals 2, they're both present. All right? We agree with that? Okay. Well, that's pretty much the only thing there is to realize. And let me just zero in on 2 of those convergences. These are the same thing, but are just a subset of it that concentrates on the P greater than 2 case, basically. So reminder, again, when P is greater than 2, if there is a discontinuous component, you converge to it in a finite way, meaning that B hat has a finite limit, which is B of P, if that discontinuous component is present. If there is no discontinuous component, B hat goes to 0, and it goes to 0 at a rate which is a function of delta, and it's what's in red up there. All right? So now what's the idea? The idea is going to be really quite simple, and the idea is going to be to consider sampling at the highest frequency you have versus sampling at a multiple of that frequency. So it's a bit like a 2 time scales. It's a bit like a 2 time scales, but in sort of a different period. Okay, suppose delta n is 10 seconds. If I have data sampled every 10 seconds, then I have data sampled every 20 seconds, right? Just take every other observation. At the cost of cutting down my sample size in half, I can definitely sample every 20 seconds if I can sample every 10 seconds. Now, let's ask yourself what happens in that convergence if you take the ratio of b hat sampled every k delta n divided by b hat sampled every delta n. So the ratio of sampling every 20 seconds divided by sampling every 10 seconds for the p variation. If there are jumps, let's go back one slide, whoops. If there are jumps, they both converge to the same limit. And when delta n goes to 0, k delta n also goes to 0, when k is finite, k is 2, say. They both converge to the same limit, so obviously, to the same non-zero limit, so obviously the ratio in probability converges to 1. So if there are jumps, the ratio converges to 1. If there are no jumps, they both converge to 0. So it may seem crazy to take the ratio, but it's not too crazy because the ratio converges to 0 at different rates. And the rate is given here. Clearly, when you take the ratio, you see that you're going to get a factor k to the power 1 minus p over 2 as becoming the limit in that ratio. Or rather, since you get the ratio on the other side, it's k to the power p over 2 minus 1 becomes your limit. So in other words, if there are jumps, you have two things that converge to 1. You have two things that both converge to the same thing. You take the ratio that converges to 1. If there are no jumps, they both converge to 0, but they converge to 0 at different rates. And the ratio is just a scalar multiplicative of those rates. So that's all there is to the idea. It's pretty simple. And you end up with that different limit, 1 for the ratio if there are jumps, and k to the power p over 2 minus 1 if there are no jumps. Now in the introduction I announced 1 and 2. So the way you get 1 and 2 is by taking k equals 2 and p equals 4. You need k, clearly k is an integer greater than 1. So you take 2. Why 2 and not 3? I'll discuss that in a moment. And p, you need p greater than 2. Now, to get convergence in probability, you need p greater than 2. To get the central limit theorem so that you can write a test statistic, you need p greater than 3. And so you could, if you really wanted, you could take 3.1 or 3.2 or 3.5, but I guess an integer is a more natural value, so we took 4. Okay? And then you take 2 to the power 4 over 2 minus 1, that gets you 2. So that's how you're getting 1 or 2. So testing for jumps, we need rates of convergence, asymptotic variances, and basically the rest is sort of, the rest is basically, getting those distributions in place. It's a technology that, as I indicated, you need p strictly greater than 3 to get a central limit theorem. But basically, it's a technology that one needs to basically employ once and then sort of see how it goes and then try to make it work for that particular case. Okay, so that's the asymptotic distribution. There are consistent estimators of the variances, so these things are standardized. Practical considerations in terms of applying this. There's a natural tendency to think that since the limit are 1 or 2, or if you take k equals 3, so if you don't sample 20 seconds versus 10 seconds, but you sample 30 seconds versus 10 seconds, then k is 3. So now the limits become 1 and 3. So you might say that might be a good idea because then it's easier to separate 1 from 3 than to separate 1 from 2. The problem is that this rate of convergence of the test statistic depends upon k because if you try to separate 1 from 3, then you've sampled every 30 seconds. So now you've reduced your sample size even more. By sampling every 30 seconds, you cut down your sample size. So you have a bit of the same effect that I described yesterday, in that as you reduce your sample size by downsampling, that's not good. That sort of reduces the rate of convergence of the estimator as usual. And so it's better, in fact, to take k equals 2 rather than higher values. If you can just do a root mean squared error calculation, if you will. Okay, so here are some simulations. I'm going to take t equals 1 day. I'm going to sample at very high frequency. That's because I take t equals 1 day. If I took t equals a month, I could afford to sample less frequently. So I'm sampling every 1 second, or every 5 seconds, as you will see. And under the null of no jumps, here's what happens when you have k equals 2 and k equals 3. So if there are no jumps and k is 2, the statistic should go to 2. If there are no jumps and k is 3, the statistic should go to 3. And that's what it does. It's between 1.9 and 2.1, between 2.8 and 3.2. You see naturally that at k equals 3, you get a higher dispersion. That's what I was describing, because at k equals 3, you have a lower sample size than at k equals 2. And the standardized distribution look very normal, as predicted. If you simulate with compound Poisson jumps, plus Brownian motion, of course, you're getting a limit which is 1. And here you have compound Poisson jumps that have an arrival rate of 1 jump per day on average. So the lambda of the compound Poisson is calibrated to give you 1 jump per day. And on the right-hand side, it's calibrated to give you 10 jumps per day, and it doesn't really make a difference. So you can basically, as soon as there's one big jump, you will just pick it up, and it will be there. So it dominates. Now, of course, when I say 1 jump per day, if you simulate a Poisson process, which on average gives you 1 jump per day, a few of the times you're going to have 0 jumps. That's the only way you can have 1 jump per day on average. So sometimes you get 0 jumps. Now when you have 0 jumps, I'm throwing those paths out. Why? Because remember, this is a test of not whether jumps are possible or not. It's a test of whether jumps occurred or not. So that's exactly an example of the peso problem. You have a Poisson process that can generate on average 1 jump per day. In very many days, it's not going to jump at all. And when that happens, I will say there was no jump. And so I resimulate to get at least a jump. So that means that in sample, all my samples contain at least a jump by construction on my left-hand side, over there. Now, if you simulate from Cauchy jumps, now these guys jump all the time. So there you have no peso problem with those, and you get 1. Now, interestingly enough, what you get is you get a very non-normal distribution, but once you standardize, things become normal as predicted by the central limit theorem. But what you see here is that really the estimate of the asymptotic variance has a lot of work to do to restore normality. I mean, it's quite, because you go from really bizarre tails to the rows in the row statistic to really nicely standardized tails, which are normal in there. And what is theta? Theta is the scale parameter. Theta is the scale parameter of the Cauchy process. So it's the scale parameter of the jump process. So it's like sigma for Brownian motion, basically. Now, what happens here if you don't throw away the paths that have no jumps? In the case of a Poisson process, that's what's on the left-hand side. Then if you do 1 jump per day, including the paths where there were no jumps, then you end up with the picture on the left, which is very clearly bimodal. Because what you have is on the left-hand side, centered around 1, you have all the paths that had at least one jump. And then on the right-hand side, centered around 2, you get all the days where there were no jumps. So all the days where there were no jumps in the market, you end up being around 2. All the days where there were at least one jump, you end up being around 1. In the Cauchy case, as I said, a Cauchy process will always jump. So you don't have that problem. But you can make the jumps very, very tiny by reducing the parameter theta. Right? If you reduce the parameter theta, it's like in the Brownian motion case, if you reduce sigma, you are making the increments of the Brownian motion smaller and smaller. And what I'm showing you here on the right-hand side is what happens if you simulate from a Cauchy process where the jumps are killed by a scaling parameter that makes them really, really small. Right? And what you end up is something that's all over the place. You end up with a situation where you just really can't tell. Because the jumps are so small, yes, mathematically they are jumps, but you've killed them by taking a theta parameter that is so small that you are really, often you are around 1, but sometimes you're around 2, and then you can be anywhere in between as well. So you end up with sort of that situation where you really can't tell. So you can view this as being sort of a poor man's power calculation, basically. What you do is you take a sequence of alternatives, and you're saying, well, in my sequence of alternatives, when theta converges to 0, when the scaling parameter of the Cauchy process converges to 0, then I can't do anything. Okay, now, I am preempting the question here that I know I would otherwise inevitably get, which is, hey, you use something every 5 seconds, 15 seconds, and what about the noise? Well, yes, there is noise in the data. There is market microstructure noise in the data, so what happens in this case? Well, here's what happens in this case. What happens in this case is that the test statistic, if you have additive noise, the limit of the test statistic in the case where p equals 4, which is what we implemented, is no longer 1 or 2, but it's 1 over k, which if k is 2 becomes 1/2. So in other words, if there is market microstructure noise in the data of the additive kind, then you get 1/2 as your limit. It's no longer 1 or 2, but it's 1/2. Now that's nice, because at least it's not 1 or 2. So you can distinguish that. You can distinguish that from 1 or 2. We've done another calculation, which is not under transparency here, and in fact is not in the paper. But if your noise, instead of being additive, is a rounding error noise, which means that what the price you're observing is the rounded version of the price rounded to, for example, the nearest cent. Then the limit becomes 1 over square root of k, which in this case becomes 1 over square root of 2, or about 0.7. So it's another number that's also to the left of 1. So keep that in mind, that the limit is now to the left of 1, and it could be different values to the left of 1 depending upon the exact nature of the noise. If you have IID noise or not IID noise or rounding error noise or something else. So keep that in mind when you look at the following plot. The following plot shows the following exercise. So what we did here was we took every trading day in 2005, there were I think 250 of them, and we took all 30 stocks in the Dow Jones. Okay, that's the 30 biggest ones, the 30 most liquid ones, and took all of them, and we treat each day, each stock, as an independent experiment. So there are 30 times 250, that's about 7,500 experiments. And each day, each stock, we calculate the test statistic, and then we do a histogram of the values we obtain. Okay? So kind of that's like an average behavior of those stocks over that year. And the 4 plots correspond to 5 seconds, 10 seconds, 15 seconds, 30 seconds. And what do you see? At 5 seconds, which is the upper left corner, you see a lot of evidence of numbers below 1. What's that? That's market microstructure noise. Okay. As you move to 10 seconds and 15 seconds, you start to get to something that looks like it's centered around 1, which is really evidence of jumps. With, of course, still noise present, but sort of the left tail starts to come down. As you go to higher frequency, still relative, 30 seconds is not very, as you go to lower frequency, 30 seconds, what you end up is you end up seeing kind of the left tail is still there, but it's no longer as big, and then things get more diffuse between 1 and 2. And what's going on there is a bit of the time smoothing effect that I described this morning, except in a less extreme version of it. In a more extreme version, if you like, at sort of much higher frequencies than just looking at the crash of 1987 in between daily and annual frequencies. So what you end up with is, so if you look at those sort of 4 plots through that lens, I think you can tell a story that makes sense in terms of what the various limits are and what we expect to see happening. Now, if you ask yourself about what kind of jumps would get averaged out over 30 seconds, clearly those have to be very high activity jumps. You can't tell a compelling story for why you would have multiple compound Poisson process jumps, big jumps in a 30-second time window. So that's really sort of pointing out towards infinite activity jumps all by itself. If you interpret that picture in that spirit, and that kind of leads me into what I'll talk about this afternoon, which is trying to say something about the degree of activity of jumps. But that picture is already indicative of what's going on in the data, which is that, at ultra-high frequency data, at ultra-high frequency in the upper left corner, the noise dominates. As you go to sort of the intermediary frequency where you sort of try to escape from the really, really high frequency noise, but not quite get in the realm of things where you average things out, then you get really evidence for jumps. As you lower the frequency further from there, things become, now you start getting more evidence for continuity, but that could very well be the averaging out of those jumps, because that's the way you can reconcile the difference between 10 seconds and 30 seconds, or 10 or 15 seconds and 1 minute, for example. Okay? That's kind of what the data looks like. And I guess this afternoon we'll sort of look at the question of, well, how active are those jumps? I think it's pretty clear that there are jumps in the data, because this thing looks clearly more towards 1 than towards 2. No matter how you interpret this, this is more towards 1 than towards 2. Then the question becomes, what kind of jumps are those? Are they compound Poisson jumps, or are they infinite activity jumps? And again, if you keep in mind that there is some averaging out that takes place even at 30 seconds, then that sort of points towards the presence of really infinite activity jumps in the data. And indeed, that's what we'll find once we have a formal way of thinking about that, not just an empirical way based on comparing those 2 plots. So that's it for this, for testing for jumps. And I guess we are breaking until, is it 2:30? Until 2:30. Happy to take any questions now. And when we resume at 2:30, we will talk about estimating the degree of activities of jump.
You said that the value of the test statistics for additive noise is about 1/2, and for multiplicative noise about 1.7 or something like this. So could I...
0.7.
0.7, yeah.
Right.
So
Not
could I...
multiplicative noise, rounding noise.
Right, yeah, rounding noise. So could I use this to check how much noise is in the data at the different frequencies?
To some degree you could, although if you look at this picture, it doesn't give you a quantitative answer. You can't translate that picture into an estimate for what I called yesterday A, which was, the standard deviation of the noise, or equivalently an estimate of the quantity of noise that is in the data. But what the picture is indicative of, the fact that you have this big fat left tail in those histograms is indicative of the fact that noise is a problem in the data.
Is it also indicative of at 30 seconds I don't have that much noise anymore?
To some degree, yes.
Okay.
Yes. The fact that, it's less of a problem at 30 seconds, but it's still not gone though, as you can see.
Okay, thanks.
Have you checked if this testing procedure is consistent with the other one for the smiles? Like you get smiles for the first, you get jumps for the first one, and you don't get jumps for this one. And you have like a test for the other one. You can even take different maturities, right? 1 month, 3 months, right. And it should be consistent because it's the same process.
Every test that I've ever done on financial data, different ones. Obviously, you can't do it on the same data because by construction they are very different data. This is high frequency observations on an underlying asset. The other one is, options observations of the same asset. So they're not the same data. But every test that I and others have done using their own methodologies all end up with the answer that they are jumps.
So that's a killer for Heston and local volatility models?
Certainly my test from this morning cannot rule out a multivariate model without jumps. I think I stressed that you could rule out a univariate model without jumps, but it's the argument of going this way versus going around, right? In 3 dimensions, I can go around that path without crossing. But, it sounds pretty clear that there are jumps in the data, frankly.
Thanks.
Especially if you allow for high infinite activity jumps. In any given sample size, you may not find compound Poisson jumps, but you will probably find high infinite activity jumps. Yeah, Marcus has a question over there.
So my question, perhaps put in a naive way, would be, I'm a practitioner, I apply your method, I calculate the test statistics, I get out a value 1.2, let's say. What is the answer? Well, so to put it differently, you told us this morning very precisely, we cannot distinguish between jumps and not jumps because we can approximate arbitrarily well the jump model and the pure diffusion model. Right. So the idea would be, could we have some kind of hypothesis, alternative, some kind of separation, which depends on the number of observations, perhaps?
So these are non-standardized test statistics. If you want a formal answer to the question, then clearly you need to look at standardized test statistic and not say whether it's 1.2 or something, but say how it compares to a normal distribution after having estimated the standard deviation. So the reason I'm looking at the data this way is because I can tell you a story about what happens to the left of one, what happens around one, what happens there, that I can't tell if I standardize things. So that's the first thing. The second thing is the power calculation. Those simulations I showed earlier about the theta, the Cauchy process with killing the theta, that was a way of taking an alternative model and converging it towards the norm. Another one would be the one I think you have in mind, where you take, like this morning, you take alpha going to 2 in the stable class of processes, for example. Yet another one might be to take a compound Poisson process and drive up its intensity and drive down the size of the jumps in such a way that you can also converge. So we have not made any formal power calculations, At the same time, I feel that there are now so many jump tests out there that maybe it's time for someone to actually sit down and, and do those formal power calculations. I think that would be a really interesting project. It's not something we've done, but it would be quite interesting to just figure out what is the right, what is the actual power of those different tests for. I suspect you're going to get different answers depending upon the sequence of alternatives you have in mind. And converging to a Brownian motion, by being compound Poisson with intensity that goes up, size that goes down, or converging by being any Levy process with scale that goes to 0, or converging by being a stable with index that goes to 2, those are very different ways of converging to a Brownian motion, into a continuous process. I don't know that you would necessarily get the same answer from different tests, but it would be very interesting, for sure.
Okay, so thank you very much. And perhaps just a remark concerning your first part of this session. I mean, you're having this test statistics depending on the cross derivative of the transition probability. Right. And you apply this to option price data. I think you should be honest to say, in order to come down to this test statistics, you have to differentiate four times. To come from option data to the state price density, you differentiate twice. That's Again, right. You differentiate twice, and this might be very unstable. So also there, you should not only point out some kind of test statistics, but the confidence bands will be huge. So
that's a very good point. Thank you for making it. So let me just come back to this. So what I did here, and you're absolutely right. If you implement this non-parametrically, so if you fit a model for the SMILE, or equivalently a model for the pricing function that is non-parametric, then you differentiate it twice non-parametrically to get to the state price density. I didn't write down the equation, but everybody, I'm assuming, is familiar with the fact that the second cross derivative of the core pricing function with respect to the strike ends up being e to the plus r tau, the density. And then, as Marcus pointed out, then you take the log of that and you differentiate it twice again. So if you do it non-parametrically, you differentiate it twice, and in non-parametric regression, you pay a price in rate of convergence for every additional derivative. So differentiating twice is pretty bad. So in fact, the way I implement this test, and I'm helped by the practitioners, is that those practitioners, because they all trade on the same parametric model, I implement this test parametrically. So when you see that picture, this is a parametric fit of the implied volatility. And in fact, it's almost a perfect fit, because this is self-fulfilling prophecies. These guys all trade on the basis of the same parametric model, then I get the data from the market. The data plot exactly on the model they all use. So if I had done, so there's a reason why, so if you look at the paper, in the appendix, there is a treatment of how the test would get done non-parametrically that accounts for the right weights of convergence and so on, but that's not the way I implement it, because you're absolutely right, it would be crazy to go and differentiate 4 times. Your non-parametric regression function. So it's done parametrically.
Okay, thank you.
Okay, I have also a question on this result. You use this S&P 500 option data. So aren't the results conditional on your viewing the S&P 500 as a one-dimensional process? Mm-hmm. So couldn't you generate such smiles saying you have a basket of options and or of stocks and continuous time processes and just a certain overall dependence structure in the basket that generates this result?
Yeah, I can't rule out that what you're describing is what's happening. Okay. So I'm not saying there are jumps. What I'm saying is it's impossible to write a univariate model without jumps for those data.
Maybe it's just a common jump component, but
Possible. Yeah. I mean, if you think though, in terms of the economic story behind it, I think market participants would tend to, if you ask them point blank, why are those put options on the left-hand side of that curve so expensive? They will tell you it's because it's crash insurance. And what's crash insurance? Well, it's insurance against jumps. And why are you now looking at implied volatilities on the left-hand side that is, again, I suspect it's probably above 100%. Because if you are, if you're looking at an at the money implied vol on the VIX, which is 75%, if you go 20 points out of the money, you've got to be near 100 or above 100, right? Our Deutsche Bank friends confirm that or infirm that. But you probably are, and if you think the volatility is 100% per year, you are really thinking that, right? To get an implied vol of 100% per year, you've got to be thinking about things that represent jumps. You can't, the volatility is so high because you are mixing up jumps and volatility. You are attributing all the variability in the data to the continuous process, when in fact they are jumps. In economic terms, a standard deviation of 100% per year is nonsensical.
I have a question also connected with maybe 3 pictures farther from this one. So there is this picture of the derivative of second order, yes? This one, yeah, exactly. So maybe what is the reason that it is negative in these areas between something like 700 and 900 and then okay, maybe it is a bit practical. I don't.
It's kind of, you took the density, you calculate the log, and you calculate the cross derivative, and that's what you get. I try to provide intuition when I can, but there are limits to my ability to provide intuition all the time. And I think you are testing that limit right there. I don't know. That's just what, I don't have a lot, I don't have intuition about, the way I should expect the second cross derivative of the log of the density to behave. That's just the way it is. I suppose if you really wanted to answer that question, you take a log normal density where you know what the answer is. Because the answer ends up being a flat line. And then you go from a log normal density and you do an Edgeworth expansion, right? You do an Edgeworth expansion around the log normal density with a correction for skewness and a correction for kurtosis. And you start with small coefficients. And then, based on that Edgeworth expansion, you do a Taylor series of the criterion function expressed in the coefficients of that Edgeworth expansion, and you look at the point-by-point sign of the correction terms. And what I suspect you would see is that you start from the right line, and then you would start going down at the point where the skewness happens. So that would be, if you wanted intuition to see what part of the density gets you this, is it the skewness, is it the fat tails, then you could answer that question that way. But I can't do that in my head. Okay, maybe we break and then we resume at 2:30 then.